Hello everyone, welcome to Software Reverse Engineering with Cyber Commander Yam. This course is based on my titled book, Software Reversing. Both the book and this course is recommended for all cybersecurity professionals, software engineers, hardware engineers, penetration testers, hackers, and all cyber forensic professionals. A quick introduction of myself. I'm a certified cybersecurity and cyber forensic professional with over 9 years of working experience as both a cybersecurity professional and a cyber forensic professional. I have many cyber certifications in cybersecurity, cyber forensics, networking, pen testing, Microsoft Server Administration, and software reversing. Also, aside being a cybersecurity and cyber forensic instructor, I am the author of the following cyber books. That is CySec, which is a cybersecurity courseware book, Forensic Volume 1, which is a cyber forensic courseware book, Software Reversing, which is a software reverse engineering courseware book, The Art of Cyber Warfare, a cyber combat book, The Art of Cyber Intelligence, equally also a combat cyber book, The Overview of Deepfake, which is a research work, The Code of Ethics for all cybersecurity professionals, which is a code of ethics for all cybersecurity professionals, CyOPSEC, which is a cybersecurity operational manual guideline, and lastly, Afri-Cryptography, which is a white paper based on my encryption research work. I've also assisted in solving 21 cyber-related crimes, 17 cyber forensics investigations, and out of my software engineering expertise, I have reviewed 11 software source code, all with different highly esteemed institutions. With my cyber engineering expertise, experience and technical know-how, I have made a lot of achievements from software development to hardware and networking architectural engineering. But since this lesson is not about my profile and my achievement, I will end my profile introduction here in order for us to dive straight into the lesson. Before Model 1 lesson objectives, it is important to note that the complete lesson of this software reverse engineering has been segmented into different parts based on all the tech team models that sums up to be the complete lesson of my book, Software Reversing. The following are the objectives of Model 1, which is titled Introduction to Cyber Reverse Engineering. The first objective of Model 1 is the definition of cyber reverse engineering. The second is the various forms and types of cyber reverse engineering. We will also take a detailed look at the required feeder cyber skill set for cyber reverse engineering. We will also look at who can become a cyber reverse engineer, as well as the importance of cyber reverse engineering. After the importance of cyber reverse engineering, we will also take a detailed look at the recommended guidelines to follow during cyber reverse engineering. The scope and the tasks of cyber reverse engineering then follows. Then after, the applications of cyber reverse engineering. The last objective of Model 1 will be a detailed review of all software reverse engineering tools. With Model 1 lesson objectives outlined, let's begin the class by first defining cyber reverse engineering. The term cyber reverse engineering is defined as the process or the method through which one attempts to understand the deductive reasoning on how a device, a process, a system, or how a piece of software accomplishes its task. In a simple term, a cyber reverse engineering is the process or the act of disassembling a device, a system, or a software to the core of its formation or to the core of its manufacturing design. It's important to note that the definition of cyber reverse engineering may vary depending on the form or the type of cyber reverse engineering. So as the class proceeds, I will define reverse engineering based on the various forms of reverse engineering there is in the cyberspace. Before we proceed to the various forms of cyber reverse engineering, I want to encourage you to try and perform a cyber reverse engineering on any cyber product. that is either a software, a hardware, or a network design. Don't let the term reverse engineering scare you off, since in actual fact, reverse engineering is not as difficult as many perceive it to be. In reality, we all perform a form of reverse engineering on a daily basis, but many are ignorant about they performing a form of reverse engineering or being a reverse engineer themselves. From the tracing or redrawing of an image, from the taking of measurement of a craft work in order to recraft it, from the resewing or redesigning of someone's fashion design or a fashion style, to the performing or singing of a cover song, that is, singing an already composed song but making it sound differently, are all forms of reverse engineering. So be at ease and be encouraged to try any of the forms of cyber reverse engineering, which we'll be learning into details in our next lesson. Forms of cyber reverse engineering. During my definition of cyber reverse engineering, I did state that there are many forms of cyber reverse engineering. So in this session, we will be identifying the various forms of cyber reverse engineering in the cyberspace. The first form of cyber reverse engineering is hardware reverse engineering. Hardware reverse engineering is a form of cyber reverse engineering that involves either the assembling, reassembling, or the disassembling of a hardware device to its manufacturing core. In other words, hardware reverse engineering is the reconstruction of a cyber hardware device. A hardware reverse engineering can be performed on all cyber devices, including mobile phones, laptops, television sets, cars, routers, walkie-talkies, CCTV cameras, printers, tablets, IoT devices, and all other cyber devices. The following are the various purposes for which a hardware reverse engineering could be conducted. One main purpose for which often a hardware reverse engineering is conducted is to aid in cyber forensic investigations. A hardware reverse engineering is of utmost importance in a cyber forensic investigation that involves damaged devices like a laptop, a mobile phone, a solid-state drive, desktops, walkie-talkies, printers, tablets, or data acquisition from a damaged hard drive. From an experience point of view, my ability to perform a hardware reverse engineering on an intentionally damaged mobile phone in order to reconstruct the damaged mobile phone for its data acquisition, which was very instrumental to the finalization of the cyber forensic investigation. For this reason, I urge you to acquire more practical hardware reverse engineering skills, technical know-how, and knowledge. As the lesson proceeds, I will be demonstrating a practical session of a hardware reverse engineering on a mobile phone, since this lesson is more practical than theory, so I urge you to stay tuned for more practicals. Another purpose for which a hardware reverse engineering could be conducted is for a cyber research purpose. A perfect example of a hardware reverse engineering being instrumental in a cyber research work is that of the cyber intelligence research work conducted by the United States Department of Defense on some of the Chinese manufactured devices, including Huawei devices that the United States security agencies were using. During this particular research, hardware reverse engineering was very instrumental to the research team in the disassembling and the reconstruction of some of the sampled devices, which during the research process proved with evidence that most of the Chinese manufactured cyber devices often gathers data from its user to a remote server in China. Based on the findings of this cyber research work by the United States Department of Defense, which proved the theory of the US about the Chinese government gathering intelligence relating to security, telecommunication, health, and cyber intelligence through most of the Chinese manufactured devices, couldn't have been proven without the expertise and input of hardware reverse engineering. Networking reverse engineering is another form of cyber reverse engineering in the cyberspace. Network reverse engineering is the act of either extracting or the reconstructing of a network environment in order to understand its deductive functioning. Networking reverse engineering is sometimes referred to as protocol reversing. Let's take a look at some practical examples and some field applications of networking reverse engineering in the cyberspace. One practical application of networking reverse engineering is in the field of networking incident forensic investigation and in a network security research. A practical example of a network security research project that involved network reverse engineering is the network security research conducted by the Systematic Anti-Malware Company, which discovered the world's most sophisticated network malware attack, popularly referred to as Starknet by civilians. The last and the most popular form of cyber reverse engineering is software reverse engineering. Software reverse engineering is the most popular form of cyber reverse engineering because it's the most commonly performed reverse engineering in the cyberspace, since every component that forms a cyber system requires a software for its functionality and integration with a cyber system. Software reverse engineering is defined as the process of analyzing a software system either in a whole or in a part in order to extract its design and its implementation information. In other words, software reverse engineering is the act of disassembling a software to its core source code. In terms of its uses, software reverse engineering is often performed to either detect, determine, or to neutralize the functionality of a malware or a virus, and is also used as a form of security mechanism to protect the intellectual property of a cyber system. It's important to note that software obfuscation is not the same as software reverse engineering. So, as the class proceeds, we'll be learning the difference between software reverse engineering and software obfuscation. The next session is about the cyber skill set required to perform the various forms of cyber reverse engineering. Cyber reverse engineering skill set. With the various forms of cyber reverse engineering outlined, let's proceed to identify some cyber skill sets, experience and technical know-how required to perform any of the forms of cyber reverse engineering. The following are the required cyber skill set, experience and technical know-how for all forms of cyber reverse engineering, that is, hardware reverse engineering, networking reverse engineering, and software reverse engineering respectively. For hardware reverse engineering, you must have in-depth knowledge, experience and technical know-how in both hardware and electronic engineering. Since as a hardware reverse engineer, you will be required to either remove or replace a hardware component with a soldering iron. A hardware reverse engineer is also expected to have some in-depth knowledge in semiconductor device physics, as well as knowledge of closed-loop control and adaptive algorithms. You must also have good understanding of kernel-level coding, debugging, and device drivers functionalities. For experiences, a hardware reverse engineer is expected to have some level of experience in programming, specifically in macro and script development experience. Aside macro and script development experience, a hardware reverse engineer is expected to have experience in both macro photography and photo editing or annotation for the purpose of evidence gathering and report writing. For professionalism, a hardware reverse engineer is expected to have strong analytical, research, and problem-solving skills. For the purpose of report writing and effectiveness, hardware reverse engineers are expected to be result-oriented and as well as are expected to have excellent writing and verbal communication skills for the purpose of being able to succinctly compile and compose written reports. For the purpose of understanding and the ability to identify the various types of motherboards and as well as the ability to read a motherboard, a hardware reverse engineer ought to have in-depth knowledge in both 32-bit and the 64-bit motherboard architecture model, and as well as the in-depth knowledge in the ARM assembly instructions. Experience with application and technology used in electronic products such as MEMS, sensors, haptics, wireless, radios protocols, audios, autofocus, optical image stabilization, voice coil, other various motor drivers or controls, the USB, and other serial bus protocols is a must for all hardware reverse engineers for the purpose of being able to interpret the functionalities of any identified drivers on a motherboard. For the purpose of being able to identify and replace faulty electronic components, a hardware reverse engineer is expected to have both in-depth knowledge, understanding, and the ability to conduct a complete analysis of an overall system, subsystem, and specific ICs for electronic devices in the categories such as smartphones, tablets, hearables, wearables, smart home devices, and automotive infotainment devices. The ability to repair, disassemble, and reassemble a cyber device is one of the basic requirements for hardware reverse engineers. This is because hardware reverse engineers are often required to either repair a faulty device, which in the process requires the dismantling or the disassembling of the faulty cyber device. The last must-have cyber skills of a hardware reverse engineer is the desire and the attitude to learn new hardware technologies, and as well as to conduct hardware research findings in order to always be updated with the new and the current trends of hardware components and designs. To be honest with you, I admit that the required outlined cyber skill set and experience expected of a hardware reverse engineer is so demanding and so much. But on a more lighter note, the outlined experiences and cyber skill set can easily be attained by either taking a hardware engineering professional course or through self-learning and research. So don't be discouraged. You can acquire all these required cyber skill sets of a hardware reverse engineer within the period of 6 months or a year. That is only if you are determined and willing to. It's important to note that this outlined cyber skill set and experience will not only equip and aid you to perform hardware reverse engineering, it will also equip you to be an excellent cyber forensic professional and a very good hardware engineer and a repairer. So for these reasons, I intrigue you to take a hardware engineering professional course. Note that this outline required cyber skill set for hardware reverse engineering is just to mention a few, since there are other required hardware reverse engineering skill sets expected from hardware reverse engineers. For networking reverse engineering, the following are the must-have required cyber skill sets, knowledge, experience, and technical know-how expected of a networking reverse engineer. One of the basic and the first required knowledge and technical know-how expected of a network reverse engineer is the in-depth understanding of transmission control protocol and the user datagram protocol. Having in-depth knowledge in both TCP and UDP will enable you as a networking reverse engineer in the identification of transmission control protocols and the user datagram protocols of a network. Still on protocols, networking reverse engineers are expected to know how to perform both transmission control protocol and user datagram protocol sniffing, eavesdropping, and the reconstruction of both transmission control protocol and user datagram protocol of a network. Networking reverse engineers are expected to know how to build and set up a networking lab for the analyzing and extraction of real-time transport protocol data from a voice-over Internet protocol network. The ability to analyze and extract real-time transport protocol data from a voice-over Internet protocol will enable you as a networking reverse engineer to reconstruct original messages of a voice-over Internet protocol from the extracted real-time transport protocol data of a voice-over Internet protocol. Another required cyber skill set of a networking reverse engineer is the in-depth knowledge, experience, and technical know-how of a network penetration testing. Also, the experience and technical know-how in networking protocols, and networking security infrastructure are all required and expected of a networking reverse engineer. The last must have networking experience and technical know-how expected of a network reverse engineer is the use of network traffic analysis tools like the NetFort LAN Guardian tool, the SolarWinds network traffic analysis tool, Wireshark, and the NetFlow Analyzer, just to mention a few. Although the above outlined required networking experience and technical know-how appears to be so much, All can be acquired within a period of a year by either taking a networking engineering professional course or through self-learning, only if you are willing and determined. Note that the listed required networking engineering skill sets for networking reverse engineering doesn't represent all the required and the must-have networking engineering skill set expected of a networking reverse engineer. Having the following in-depth knowledge, experience, and technical know-how in networking engineering will not just equip you to perform a networking reverse engineering, but it will also equip you to be an excellent networking forensic investigator. For software reverse engineering, the following are the required software engineering skill sets, experience, and technical know-how needed to perform a software reverse engineering. The first and the basic must-have software engineering skill set required for the performance of software engineering is the experience and technical know-how in programming. In other words, the ability to read, understand, interpret, and to communicate with a computer via a computer language. Since software reverse engineering involves the act of reading to understand a computer language and its functionality, software reverse engineers are required to be proficient in most of the commonly used computer programming languages and script languages like PHP, HTML, Python, C#, Ruby, Perl, Pascal, Basic, Java, COBOL, C++, the C language, JavaScript, Go, SQL, the Swift language for Apple-based apps, just to mention a few. Being proficient in most of the commonly used programming languages and scripting languages will enable you as a software reverse engineer to perform any form of software reverse engineering on most of the commonly used programming languages or scripting languages. Note that the total number of officially used programming languages that exist in the cyberspace is approximately 9,000 programming languages, and just 50 out of the 9,000 programming languages are commonly used and the most popular programming languages in the cyberspace. For this reason, no one is expected to be proficient in all the 9,000 computer programming languages and the 50 commonly used programming languages in the cyberspace, as there is no record of any human being able to speak all the world languages or 50 recognized international languages. But for the purpose of being effective and productive software reverse engineer, I highly recommend you to be proficient in at least 3 or 5 out of the 50 commonly used programming languages, but must have at least the basic concept and understanding about most of the commonly used programming languages in the cyberspace. Second on our list of the must-have experience and technical know-how required of a software reverse engineer is the in-depth knowledge and the deep understanding of firmware and binary disassembling. Since the knowledge, understanding, and technical know-how of a firmware and binary disassembling enables software reverse engineers to perform reverse engineering on a firmware binary-based software and a motherboard. Third on our list is the in-depth knowledge, understanding, and experience of the functionality of both a 32-bit, 64-bit, and the ARM assembly instructions and architecture. Having in-depth knowledge and understanding of the functionality of both 32 and 64-bit architecture and the ARM assembling instruction will enable you as a software reverse engineer to be very effective and productive in the performing of software reverse engineering on a circuit board or a motherboard. The advanced understanding of operating system terminals and Windows APIs is also recommended and expected of all software reverse engineers in order to be able to perform a reverse engineering on all the operating system platforms, that is Windows, Unix, and Linux. All software reverse engineers are also expected to have experience in both SQL and NoSQL data storage solutions, and as well as the experience and technical know-how in Elasticsearch and analytic engines to include data implementation and designs. The sixth required software reverse engineering technical know-how expected of a software reverse engineer is the experience and technical know-how in security data characterization standards such as STEX, MAEC, TAXI, and Cyberbox, especially for the analyzation of malware and backdoors in a software source code. Also, the experience in networking, network protocols, and security infrastructure is also expected of all software reverse engineers, to enable them to function and execute a software networking reverse engineering project. Another software reverse engineering experience expected of all software reverse engineers is the experience in malware analysis and identification, especially Trojan's malware. The experience in the creation and the maintenance of rules for the detection of malwares and malicious activities in a software source code is also a basic requirement for all software reverse engineers. To aid in malware analysis, which we'll be having a practical lab session on as the class proceeds. It's important to note that the ability of a software reverse engineer or a software engineer to identify malwares and even a zero-day exploit is highly dependent on the in-depth knowledge, experience, and technical know-how in malware architecture, analysis, and functionalities. So I highly recommend you to take the study of malware analysis very serious, since about 99% of software reverse engineering is performed on the basis of malware identification. The 10th on our list of recommended and required software reverse engineering skill sets is the demonstrable experience in working with an open source or a commercial analysis tool like decompilers, disassemblers, debuggers, system internal utilities, and network traffic analysis tools for the purpose of malware reverse engineering. The last requirement and my recommended software reverse engineering experience expected of all software reverse engineers is the experience in enterprise-level sandbox tools and the familiarity of edge and endpoint protection systems. Both the technical know-how and experience in the usage of sandbox tools makes it easy for software reverse engineers to operate in all sandbox virtual tools. Since software reversing is always and highly recommended to be conducted in a sandbox tool, in order to avoid the infection of a host-based operating system with a malware, that is, if the software undergoing the reverse engineering is injected with a malware. Just like the other cyber skill set requirement for both hardware and networking reverse engineering, this long-listed skill set requirement for software reverse engineering may appear to be very demanding, but from experience I can say that you can acquire all these required software reverse engineering skill sets through self-learning and determination or by taking a software engineering professional course. So don't be discouraged by the long-listed software reverse engineering requirement skill sets, technical know-how, and experience. Note that having this experience, in-depth knowledge, and technical know-how will not only just make you an excellent and productive software reverse engineer, it will also make you a resourceful cyber forensic investigator, a cyber security researcher or engineer, a penetration tester, or a software licensing expert. So for these reasons, I encourage you to pursue and acquire these software reverse engineering cyber skill sets in order to be productive, resourceful, and functionable not only in the field of software reverse engineering, but also in other cyber career fields like cyber security, cyber forensic, networking engineering, and even in the field of hardware engineering. For the purpose of you researching more about all the required cyber skill sets, experience, and technical know-how of software reverse engineering, networking reverse engineering, and hardware reverse engineering, the following is an assignment I would like you to try your hands on. Who can become a software reverse engineer? Since this Master Cyber Reverse Engineering course is really about software reverse engineering, the rest of the lesson henceforth will be more focused on software reverse engineering. But for the sake of better understanding and the integration of software reverse engineering in both networking and hardware reverse engineering, I'll be including both hardware reverse engineering and networking reverse engineering in our practical lab session. Based on our previous lessons, that is, the various forms of cyber reverse engineering and the recommended cyber skill set and experience required by the various forms of cyber reverse engineering has been outlined, Let us now proceed to identify who can become a software reverse engineer. Anyone with at least a mid-level of experience, knowledge, technical know-how, and the understanding of commonly used programming languages and scripting languages can become a software reverse engineer. But note that though software reverse engineering mostly involves software, being knowledgeable and having some level of experience in the field of hardware engineering and networking engineering will aid and equip you to be a resourceful, productive, and effective software reverse engineer. Since software reverse engineering is always conducted on a hardware device and communicated via a networking platform. To simply put, an effective and productive software reverse engineer is one who is not only knowledgeable in software reverse engineering, but also have some level of experience and technical know-how in both networking engineering and hardware engineering. Having some level of knowledge and technical know-how in both cybersecurity and cyber forensic are both great add-ons to software reverse engineers. For the recommended and required knowledge, technical know-how, experience, and the skill set for software reverse engineering, check out my lesson on the recommended cyber skill set for cyber reverse engineering. Concept and processes of software reverse engineering. The concept of software reverse engineering simply refers to the processes involved in software reverse engineering. In other words, the overview of software reverse engineering. For the easy understanding of the processes involved in software reverse engineering, let us first identify the various forms of software engineering. The first form of software engineering is forward engineering. Software forward engineering is basically the normal systematic procedure involved in the formation and development of a software. In other words, the software development lifecycle. Though the software development lifecycle have been grouped into 7 phases, namely the planning phase, the analysis phase, designing phase, development phase, the testing phase, the implementation phase, and the maintenance phase. For the purpose of software reverse engineering, the 7 phases of software development lifecycle is categorized into 4 main phases. That is, the requirement phase, the analysis phase, the design phase, and the implementation phase, respectively. Using the 4 categorized phases, simplified out of the 7 phases of the software development lifecycle, to represent forward software engineering, before a software is developed, a software developer is first expected to gather requirements about the software. The requirements may include the expected functionalities of the software, the capabilities of the software, the required technological resources needed for the functionalities of the software, and the expected graphic user interface of the software. After the gathering of all necessary requirement details, the software developer is then expected to analyze the gathered requirement details in order to design a complete and comprehensive software, which is expected of him. Design in this context is the full development and completion of the software. Upon the full development of the software is then moved into the implementation phase, which includes the software testing, the piloting of the software, and the full deployment of the software to its maximum usage. Back to the various forms of software engineering. The second form of software engineering is reverse engineering. Reverse engineering, in the context as a form of software engineering, is the act and processes involved in reverting a completely designed software to the core of its source code. As forward engineering involves the systematic procedure of a software development, that is, from the requirement phase to the analysis phase, then to the design phase, and then lastly to the implementation phase, reverse engineering have its systematic procedure beginning with the implementation phase. then to the design phase, then to the analysis phase, then lastly to the requirement phase as its systematic procedure. The implementation phase, which is the fully developed software in reverse engineering, is the phase where informations such as the basic functionalities of the software, the graphic user interface design of the software, the system requirements of the software, and the information regarding the specification of the software is gathered by observing and using the fully developed software. It's important to note that the outlined gathered information about a software to be reversed provides a software reverse engineer with the overview of what to expect during the software reverse engineering process, and also provide the reverse engineer with a better understanding of the workings and the functionalities of the software that will be reversed. Proceeding to conduct reverse engineering on a software without having the understanding of how the software works and its overview will affect the final findings of the reverse engineering and may even make it very difficult to read meaning into the source code and its structure. So for this reason, I highly recommend you to always understudy the software to be reversed in its fully operational form before beginning with the analyzation of its source code. The next phase, which is the design phase, is the phase where a structure chart in the form of a flow chart is identified and designed in order to determine and record the processing details of each model of the software structure in a procedure flow chart using a structured language like a decision table. From the identified design structure flowchart, a set of data flow diagrams are derived to show the flow of data among the processes for record. It's important to note that the processing design of a software is attained from the source code of the software to be reversed. To simply put, the source code of a software is extracted in the design phase, but for the purpose to determine the functioning data flow processes of the software. If the main purpose of the software reverse engineering being conducted is to just either clone or redesign the software or to just copy the features of the software, then the source code of the software can be copied or cloned in the design phase. In other words, the software reverse engineering lifecycle ends in the design phase. That is, if the software reverse engineering is not being conducted for the purpose to investigate a backdoor or a malware. But if the software reverse engineering being conducted is for the purpose to review the source code or to analyze the source code for either a malicious reason or for the determination of the functionalities of the software, then the processing of the software reversing is further taken to the analysis phase. Aside for the purpose of reviewing or analyzing a software source code in the analysis phase for either a malicious reason or in order to investigate the functionalities of the software, a software source code can be analyzed in the analysis phase for the following reasons. To determine if there is a hidden backdoor in the source code of the software. Another purpose is to determine if there is a malicious injected code embedded in the source code of the software. Or to determine if there is any security functionalities of the software. That is, if the software is designed to steal data to a remote server. Software reverse engineering is sometimes conducted if there is any existence of a side effect of a software. That is, if the software is serving as a botnet or as a keylogger. Last on the list of the possibility of reviewing a source code or conducting a software reverse engineering is to crack a software. That is, to examine the source code in order to bypass the licensing process. Aside these outlined purposes for software reverse engineering and source code reviewing, there are so many other reasons for conducting software reverse engineering and reviewing of a software source code. But as an experienced and professional software reverse engineer and a software source code reviewer, I recommend you to always conduct software reverse engineering and as well as to review the source code of a software you intend to purchase or use. This is because in most of the times that I've been consulted to review a source code or to conduct a software reverse engineering, I often come across malicious scripts embedded and hidden in the software and always in the blind side of the person purchasing the software or the users of the software. So as a software reverse engineer and a software source code reviewer, I urge you to always advise corporate bodies and individuals who seek or intend to purchase a software or a hardware device to have the source code of the software to be reviewed as well as to conduct a software reverse engineering on the software. Though the lesson is really on software reverse engineering, I advise you to always conduct a hardware reverse engineering on any hardware cyber device you intend to buy, in order to be determined or to be convinced that the software or the hardware device that you are purchasing have no malicious script embedded in it or have no hidden malicious functionalities, aside its outlined purposes and functionalities. The requirement phase is the last phase of software reverse engineering. As the requirement phase in the forward software reverse engineering is used in gathering information which aid in the designing of a software, information regarding the findings and observations made during a software reverse engineering and the software source code reviewing is also gathered for the documentation, record keeping, and for the presentation of the findings of the software reverse engineering and source code reviewing in the requirement phase of the software reverse engineering. That is, if the software reverse engineering is being conducted for a commercial purpose or for a corporate institution or for a purpose of an investigation. For a standard and more professional documentation of your findings and observations made during a source code reviewing or a software reverse engineering from the beginning to the last minute of the software reverse engineering process. Narrating and explaining into details the methodologies you use and your observations during the source code reviewing and the software reverse engineering in both an audio file, written and a printed document will make your findings and presentation court admissible. It will also make it easier for non-technical individuals to be able to read meaning into your findings and documentation. With the processes involved in software reverse engineering clearly detailed out, we can now proceed to the practical lab session for a real-time software reverse engineering, beginning from the next session. Tools for software reverse engineering. With the concept and the processes involved in software reverse engineering detailed out, we are now set to set up a practical lab. But before that, let's first identify some of the tools used in performing software reverse engineering. A sandbox tool is a formal software reverse engineering tool. A sandbox tool is an isolated testing environment that enables software developers to run and test a design software and as well as to open software files that may be infected with a malware without compromising the host computer or device. To simply put, a sandbox is a concealed environment created within an operating system but separated from the host operating system environment for the purpose of either testing or running a software or for the isolation of data from the host operating system of a device. Aside the purpose of testing and data isolation, software reverse engineering and source code reviewing are both recommended to be conducted in a sandbox in order to protect the hosting operating system from being infected with a malware. That is, if in case the software being reversed is infected with a malware. For the purpose of a complete isolation, the following are my recommended sandbox tools with their key features and characteristics. The VMware Workstation 16 is my chosen sandbox tool for this lesson. Now let's proceed with the installation of the VMware Workstation 16. But first, let's download it from the VMware official website. On the official VMware website, click to open the Workspace tab, and then navigate to click on the Workstation Player tab, which will direct you to the download page of the Workstation Player. On the Workstation Player download page, click on the download button in order to download the VMware Workstation 16. For the purpose of this class, I'll be downloading the Windows version for the VMware Workstation 16, since our sandbox platform is a Windows 7 based operating system. Upon the completion of the VMware Workstation 16 download, I'll proceed to install the VMware Workstation 16 on my Windows operating system. Note that you can choose to install any of the versions of the VMware Workstation as your sandbox environment. For the purpose of our lab demonstration, And without any hesitation, I'll go ahead and agree to the terms and conditions agreement without taking much time to read through the terms and condition agreement statement. But I recommend and I advise you to always read the terms and conditions agreement statement of any software before agreeing to its terms and conditions. For a detailed explanation of the terms and condition agreement statement of a software and how it works, watch my video on data privacy. The link to the video is on your screen. There's no need to change any settings here on the setup installation page, so I'll click next. Here on the user experience settings page, I choose to decline the option to join the VMware User Experience Improvement Forum. Then I'll click next to proceed to the next page. Here on the shortcut page, I'll leave the default settings, which will create a VMware shortcut link on both my desktop and in my Windows Start folder by clicking next. Click next again to complete the installation process of the VMware Workstation 16. Now click on the Finish button to close the installation dialog box. Now that my VMware Workstation 16 is fully installed on my PC, I'll now open it in order to initiate the installation process of my Windows 7 operating system. To begin with the installation of my Windows 7 operating system, I'll click on the Create New Virtual Machine tab in order to choose the version of the Windows 7 operating system I intend to install. In my case, I will choose the Windows 7 Ultimate version. You can decide to create a password login access, but for the purpose of this demonstration, I choose not to create any password access requirement. I'll click Next in order to proceed with the installation of my Windows 7 Ultimate operating system. I'll leave the default generated name for my virtual machine. You can choose to either edit or change the auto-generated name for your virtual machine. For the purpose of complete data isolation, I recommend you to always install your virtual operating system on either a separate hard drive partition or on a removable storage device, such as a pen drive or an external drive. So for the purpose of the complete isolation of my virtual machine, I'll proceed to install my virtual Windows operating system on a removable drive. I'll leave the default allocated hard drive storage space for my yet to be installed Windows 7 operating system by clicking the Next button. This is an overview of both the hard drive allocated storage space and the hard drive component that has been automatically designated for my virtual Windows 7 operating system usage. In my case, I would like to increase the number of allocated processor by clicking on the Customize Hardware tab. For the purpose of an effective and smooth software reverse engineering, I recommend you always allocate a lot of processing power for your virtual machine. Click the Finish button when done with the changes made to the hardware component allocation in order to begin the installation process of the Windows 7 operating system. For a better user experience and VMware drivers integration with the virtual operating system, always download the VMware drivers when prompted. Now that we have our sandbox environment fully set up, let's now install a software disassembling tool. Before proceeding to outline some recommended software disassembling tools, let us take a detailed look at what a software disassembling tool is. A software disassembling tool is a computer program designed to translate a machine language into an assembly language. In other words, a software disassembling tool is a converter which converts a fully designed computer software from a computer language, which is mainly made up of zeros and ones, into human readable languages such as C++, the C language, Pascal, Ruby Pi, Python, and other programming languages. Now that we know what a disassembling tool is, the following are my recommended disassembling tools. My personal best is the Ghidra, which was developed by the US National Security Authority research team and later got declassified in April 2019 as an open source software disassembling tool. Ghidra is my favorite and my personal best because of its multi-purpose features, that is, its capabilities to function as a debugger, a binary editor, a decompiler, a recompiler of binaries, and as a software disassembling and assembling tool. For these reasons, I'll be using Ghidra to conduct our software reverse engineering. So I'll go ahead with the installation of Ghidra. Before beginning with the installation of Ghidra, let us first take a look at its installation requirements. Ghidra can be installed on the Windows platform, the Linux platform, and the Unix operating system platform, which includes the Mac OS. And because Ghidra was developed with the Java programming language, it requires the installation of at least Java Runtime and Development Kit version 11. On Ghidra's installation requirement page, you can copy to open the official link to download Java Runtime and Development Kit version 11. But I have already downloaded it, so I'll just proceed and install it. The Java Runtime and Development Kit version 11 often work effectively on Windows when it is integrated into Windows environment variable. For this reason, I'll proceed to integrate Java Runtime and Development Kit version 11 into Windows environment variable. With Java 11 Runtime and Development Kit fully installed, we can now download and install Ghidra. You can download Ghidra from Ghidra's official website. I have already downloaded Ghidra, so I'll proceed with its installation. Because Ghidra is a zipped file, it will have to be extracted, but to specifically the Windows programs file in the C drive. This is because Ghidra is not a standalone installation file. So, extracting to host Ghidra in the Windows program files in the C drive will enable Ghidra to function effectively. With Ghidra extracted into the Windows program file in the C drive, open the Ghidra folder and double-click the Ghidra round batch executable file in order to install it. Windows will then open its command prompt to initiate the installation of Ghidra. You may be prompted to integrate your Java Runtime and Development Kit version 11 into Windows environment variable. But since I have already integrated the Java 11 Runtime and Development Kit into my Windows environment variable, Ghidra will proceed with its installation. Note that Ghidra doesn't install any shortcut icon on the desktop. So for this reason, you'll be required to always open Ghidra by double-clicking Ghidra's round batch executable file in the Ghidra program folder you extracted into the Windows programs folder. With both our sandbox environment and our disassembling tool fully set up, we are now set to conduct software reverse engineering. The implementation phase of software reverse engineering. During our lesson on the concept and processes involved in software reverse engineering, I did outline all the processes involved in software reverse engineering. That is, the implementation phase, the design phase, the analysis phase, and the requirement phase, respectively. So for the purpose of following the standard procedure involved in software reverse engineering, I'll begin the software reverse engineering process with the first phase, that is, the implementation phase. But before I proceed to initiate the implementation phase, let's do a recap about the overview of the implementation phase in order for you to have a better understanding and know what the implementation phase is about. In lesson 5, which was about the concept and the processes involved in software reverse engineering, I stated that the implementation phase is for the purpose of gathering information about a software to be reversed in relation to its basic functionalities, its graphic user interface design, its system requirements, and its specification by operating the software to be reversed in its operational interface. And in terms of the importance of the implementation phase, I said it provides software reverse engineers with a better understanding of the functionalities of the software to be reversed, and as well as the overview of what to expect during the software reversing and source code reviewing. It also enables software reverse engineers to easily identify any hidden or malicious functionality or script aside the software main outline functionalities. For more details about the importance of the implementation phase, refer to lesson 5, which is titled The Concept and Processes Involved in Software Reverse Engineering. With both our sandbox environment and disassembling tool fully set up, let's now proceed to install the software to be reversed in order to gather some information in relation to its functionalities, its requirements, its specifications, its graphic user interface design, and any other relevant information that will aid in the reviewing of the source code and its reversing. The link to download the software is in the description box below. Caution and disclaimer: the software which is about to be reviewed for the purpose of software reverse engineering and source code reviewing was randomly chosen strictly for educational purposes, so please don't maliciously exploit the software for any malicious reasons. With the software to be reversed fully installed, let's begin with our information gathering. It's important to note that for the purpose of record keeping, report writing, and documentation that will be court admissible, I recommend you to always document your findings and your observations during the implementation phase with graphic evidence such as screenshots or even screen recordings. From the dashboard of the software, it's obvious that this software is a keylogger, in other words, a spyware, with its basic functionalities clearly outlined in the left panel of the menu box, which is to capture every keyboard stroke, to take screenshots of the desktop activities, the web browser activities, and the images of the user of its host computer. Aside taking screenshots and recording keyboard strokes, this software is also designed to record both video and voice over Internet protocols calls made using its host computer. So just by looking at the graphics interface of this software, we've been able to ascertain its functionalities and the category of software it belongs to, which is the spyware software category. And since this software is categorized as a spyware, we will have to look out for hidden functionalities and malicious scripts during the software reversing process and source code reviewing. In summary, based on my observations and the information I have gathered from the interface of this software, I can conclude that in terms of software functionalities, this software is designed to capture every keyboard stroke, to take screenshots of the desktop activities, to capture all web browser activities, to take videos and pictures of each user, and lastly, to record both audio and video calls made on its host computer. And aside the supposed functionalities that I have outlined, this software may also have a hidden functionalities like tracking each user and stealing each user's data to a remote server, since this is a characteristic of most spywares. Let's now explore the software for more information gathering, starting with the menu options on the menu bar. Upon clicking the File tab on the menu bar, I see 5 different options. That is, the Save Report As option, the Send Log option, the Page Setup option, the Print and the Exit option. But for the purpose of demonstration, I will randomly choose only 2 options to explore information from. The Save Report As option will be my first option. From the Save Report As dialog box, the default save option for the auto-generated report by this software is either in .htm or .html file format, which are both web page format files. Let's see if there are more save format options in the Save As type drop-down list. From the drop-down list, users have only 2 formats to save their report file in, which is in either a zip file format or a .html web page format. Based on the Save As options of this software, it is obvious that this software specification in terms of its Save As option format is either .html web page format file or a zip format file. While the requirements of this software in terms of accessing or opening its save generated report is either a zip software application or a web browser like Mozilla Firefox, the Safari browser, the Chrome browser, or any other browser that supports a .html file format is required. Back to the File menu drop-down option. Now let's choose the Send Log option as our last option to explore under the File menu drop-down list. From this display banner, it's obvious that this software requires an activation in order to be able to mail its generated report to any preferred email address. So in terms of software requirements, this software requires a form of an activation in order to be able to mail its generated report to any preferred email address. Also from this same display banner, payment is a form of specification in order to be issued out an activation code to mail the auto-generated report to any preferred email address. On the note of software activation, I know most software developers, software engineers, and software users often want to know how to crack or bypass the activation of a software. But really for educational purposes, I will only highlight the part of the source code that can be manipulated in order to bypass its activation requirement, since I wouldn't want to be sued by the software developers, as well as to also encourage and promote software developers who seek to make living out of their hard work and innovations. Let's now explore the Tool menu option. Under the Tool menu is the Settings option, the Settings Wizard option, and the Uninstall option. But again, we can't explore all the options here, so let's just choose only one option to explore. I'll choose the Settings option. From the Settings option panel, it seems that all the functionalities of this software has its own dedicated settings. But for the purpose of our illustration, I will only limit our information exploration on just few of the settings options here. But I highly recommend you to always take time to explore every option there is in the software before reversing or disassembling it. Let's begin our information exploration in relation to the settings of this software with the login settings. Based on the right panel login settings options, this software gives its users the option to adjust the login settings by choosing to save keyboard stroke logs, the logs of screenshots taken, website activities logs, clipboard capture and instant messaging activities logs. And on the screenshot settings options, the software gives users the option to adjust the time interval in relation to screenshot taking. Also, the option to control the quality of captured screenshots and the option to whether or not capture the screen of any newly opened window or capture the screen anytime a mouse is clicked. Let's make a quick glance through the rest of the settings, since this illustration is for educational purpose and not a review of the ReFox spyware. Based on my observations, doing the quick glancing through of the settings option, I noticed that both the instant messaging settings option, the clipboard activities capture settings options, the program activity capture settings option, and the computer activity monitoring settings option all have no settings options relating to it. While the webcam settings option has the same setting options as the screenshot setting option. Let's explore the View tab and the Help tab for more information gathering. Upon clicking the View tab, as clearly shown on the screen, has two options, that is, the toolbar icon option and the language choice option. But since both the toolbar icon option and the language choice option all qualifies as a specification of this software, there is no need in exploring them for more information. So then, let's move on to the Help tab, which has four listed options. That is the online frequent answered questions option, the support option, the get full version option, and the about option. Though all the outline options listed under the Help tab menu are all relevant and great source of information gathering for software reverse engineering, they are both considered as irrelevant in the case of our software reverse engineering illustration. Finally, based on my observations and exploration of the ReFox spyware for information gathering, the following are the information I have personally gathered in terms of the software's functionalities, its requirements, and its specifications. It's important to note that the following outline gathered information didn't only provide us with the overview of what to expect during the software reversing and the source code reviewing. It will also serve as an evidence in our research findings during the documentation phase. Aside providing us with what to expect during the software reversing and source code reviewing, the information gathering process also prompted us to be on the lookout for any malicious scripts or hidden functionalities aside the main outline functionalities of the software, since the software is categorized as a spyware. I hope you equally gathered your own set of informations in relation to the software's functionalities, its requirements, and its specifications. Now that we have gathered all relevant information about the software that we will be reversing, it has to be analyzed in order to know what to expect during the reversing process. That is the design phase, the second phase of software reverse engineering process. So try and analyze the gathered information in order to be able to determine and to identify the functionalities, the requirements, and the specifications of the software to be reversed during the source code reviewing, which will be our next lesson. The design phase of software reverse engineering. In this lesson, the ReFox keylogger software will be taken through the design phase, which in lesson 5 I said it is the stage in the process of software reverse engineering where a structure chart in the form of a flowchart is identified and designed based on the gathered information obtained from a software to be reversed. The structured flowchart of a software enables software reverse engineers to determine the processing details of each model structure in the procedure flowchart using the structured language like a decision table. Also in lesson 5, I did say that the executable program of a software to be reversed is converted into its source code in the design phase. So in this lesson, the refer keylogger software will be converted into its source code. For more detailed explanation about the design phase, refer to lesson 5, that is, the concept and processes involved in software reverse engineering. With our minds refreshed on what the design phase is about, let's now proceed with the conversion of the executable file of the refer keylogger software into its source code. Then later identify and design a structured chart in the form of a flowchart. To begin with the conversion of the executable file of the refer keylogger software into its source code, I'll open the Ghidra disassembling tool. It's important to note that because Ghidra is not installed with a desktop shortcut icon, Ghidra can only be opened by double-clicking the Ghidra run.batch file in the Ghidra installed folder in the Program Files folder, which is located in the Drive C partition. For the sake of better user experience, the easy use of Ghidra, and those who are new to Ghidra disassembling tool, I'll be explaining the various features of the Ghidra disassembling tool in the process of reversing the refer keylogger. By default, the welcome window of Ghidra is this tip of the day dialog box, which provides users with tips and the technical know-how on how to use Ghidra. To those who are new to Ghidra, I advise you to take some time to read through the tips in order to be able to learn how to use Ghidra and to know some of its technicalities. In order to create a new project, click on the File menu tab and choose New Project. By default, the Non-Shared Project option is already chosen. But if in case you would like to share your project with others, you can choose the Shared Project option. But since I'm working alone on this project, I will choose the Non-Shared Project. Then I'll click Next to proceed to the next page of Ghidra project creation. I'll type Refer Project as my preferred name for this project. You can choose to change the default project save location to your preferred folder location of your choice. But for the purpose of this illustration, I will maintain the default project save location. Click on the Finish button in order to create your new project. With the new project created, click on the green dragon icon in order to launch the code browser. Now click on the File tab on the menu bar and then choose the Import option in order to locate the executable file of the software you intend to reverse, in my case the refer keylogger software. On the screen now is the Import dialog, with its first option indicating the format of the software being imported. The inscription in the format column, which in our case is portable executable, is indicating that the software being imported is designed to operate on a Windows operating system. And if the inscription is executable linking format, then it means that the software being imported is a Linux operating system based software. Since Ghidra have been able to identify the version of the refer keylogger software being imported is designed to be run on a Windows-based operating system, it means Ghidra is indeed an effective and trustworthy disassembling tool. While the inscription in the language column is indicating both the programming language ID and the compiler ID used to design and compile the software being imported. The language column option appears to be inactive because Ghidra has automatically detected the programming language ID and the compiler ID used in designing the refer keylogger software. But in the case where Ghidra is unable to automatically detect the programming ID and the compiler ID of the software being reversed, Ghidra has a pool of programming language ID and the compiler ID to choose from just by clicking on the three horizontal dot button in the language column. It's important to note that without the detection or the indication of the programming language ID, the OK button would be inactive. So always make sure to choose a programming language. If in case Ghidra is unable to detect the programming language ID and the compiler ID used to design the software being imported. The next column, which is the destination folder with the inscription Refork Project, is indicating the project folder in which the software being imported will be saved. This destination folder is automatically created with the same name as the project name. While the last column, that is the program name, is indicating the name of the software being imported. You can decide to change the default name of the program name to any name of your choice. But for the purpose of this illustration, I'll keep the default name as reforkfreekeylogger.exe. Click the OK button in order to proceed with the importation of the Refork Keylogger software. On the screen now is an optional prompt to have the software being imported analyzed by Ghidra. For an automatic arrangement and the categorization of the source code of the Refork Keylogger, I'll click on the Yes button to have the source code of the Refork Keylogger to be analyzed by Ghidra. The following are the various analysis options Ghidra uses for the analyzation process of a source code. The ability to easily know which analysis option to select or deselect for the analyzation process of a source code depends on the features and the category of software the software being reversed belongs to, which in actual fact is identified during the implementation phase, that is, the gathering of information about the software being reversed. For this reason, I advise you to never skip the implementation phase. From the analysis option table on the screen, Ghidra has automatically selected the core conversation ID option because it has identified some features relating to core conversation, which we can all agree that during the implementation phase, we discovered that the Refork Keylogger has the ability to capture and record both video and audio conversations of its users and its targets. Note that the analysis options may vary depending on the type of software being analyzed. But if in case you are not sure about the features and the category of software the software you are reversing belongs to, I advise you to select all the analysis options. The fact that Ghidra has been able to select the core conversation ID analysis option, which in actual fact the software being reversed has one of its features associated with core conversations, I will leave the core conversation ID option and all other auto-selected analysis options as my selected options for the analyzation of the Refork Keylogger software. So I'll click on the analysis button in order to begin the analyzation process of the Refork Keylogger software. Let us review the importation summary report whilst Ghidra is analyzing the source code of the Refork Keylogger software at the background. First on the summary report is the name of the project, followed by the modification date, then the name of the software being reversed. The report also shows both the programming language ID and the compiler ID, as well as the least system architecture processor the Refork Keylogger supports, which is the 32-bit system architecture processor. And since the Refork Keylogger supports a 32-bit system architecture processor, it's obvious it has little endian as its byte ordering. To those who don't know the meaning of the inscription little endian, it means that the least significant byte of an integer is stored at the lowest address of the integer, while the most significant byte is stored at the highest address for data items in a 32 system architecture processor. Since this is a software reverse engineering class, I presume you should know the difference between a little endian and a big endian. So for this reason, I wouldn't go into details about the difference between a little endian and a big endian. But to those who don't know the difference between a little endian and a big endian, I advise you to research about the difference between little endian and big endian in software engineering. After the endian is the addressing size, which has been identified as 32. Next is the minimum and maximum address found in the source code of the Refork Keylogger software. Listed also is the number of memory blocks, followed by the number of found instructions, the number of found symbols, the number of identified data types, and the number of data type categories found in the source code of the Refork Keylogger. To those who have no idea about what the number of functions, the number of memory blocks, the number of instructions, the number of symbols, the number of data types, and what the number of data types categories represent, I urge you to research about it, since it's a must-know and a basic knowledge in software engineering. Also on this summary report is the name of the compiler and the programming language used to compile and design the RIFO keylogger, that is the Poland-Pascal compiler. And since Poland-Pascal compiler was used to compile the RIFO keylogger, it's obvious that the RIFO keylogger was coded with the Pascal programming language, meaning you have to be knowledgeable in Pascal programming language in order to be able to review the source code of the RIFO keylogger. Let's end the reviewing of the import summary report here in order to check if the analyzation of the source code of the RIFO keylogger is completed. Upon closing the import summary report, if in case you would like to have a look at the import summary report again, just click on the Help tab on the menu bar and then click on the About RIFO Free Keylogger option. Note that the name may appear different depending on the name of the software executable file being reversed. On the screen now is the summary report of the analyzation of the RIFO keylogger source code, which is implying that the PDB program property file is missing, and as a result, Ghidra had to skip processing of the PDB file. To those who don't know what PDB stands for, PDB is the abbreviation of Program Database, and it's a proprietary file format developed by Microsoft for storing either a debugging information about a software or a program model such as a dynamic link library files abbreviated as .dll or executable file also abbreviated as .exe. PDB files often have the extension .pdb and are typically created from source files during compilation in order to store a list of all symbols in the model with their addresses and possibly the name of the files and the line on which the symbols are declared. These symbols informations are not stored in the model itself because it requires and takes up a lot of space. You can research more about Microsoft PDB files for more detailed explanation. With the completion of the first objective of this lesson, which is the conversion of the executable file of the RIFO keylogger software, let us now proceed to accomplish the last objective of this lesson, which is to identify and to design a structure chart in the form of a flowchart. Before we identify and design a structure chart from this source code, I would like to bring to your attention that a source code of a software is often copied or cloned in the design phase. That is, if the purpose of reversing the software is to clone or to copy its source code. But if the purpose of reversing a software is to investigate it in order to know how a software has been designed to function, then the source code of the software being reversed ought to be carefully studied in order to identify, design, and to generate a structure flowchart out of it. And since the last objective of this lesson is to identify and to design a structure flowchart based on the functionalities embedded in the source code of the RIFO keylogger, let us proceed to first identify the functionalities embedded in the RIFO keylogger source code. Luckily for us, unlike most of the software disassembling tools, Ghidra has the ability to automatically identify the functionalities in the source code, just as it has automatically identified the functionalities in the RIFO keylogger source code during the analyzation process, and has also proceeded to automatically design a structure flowchart based on its identified functionalities in the RIFO keylogger source code. The identified functionalities, features, and the processes of how the RIFO keylogger works has been mapped in the left panel in the form of a program tree which represents the processes involved in memory mapping of the RIFO keylogger, and has been categorized in the form of a symbol tree which shows the symbols from a program in a hierarchical view, organized by the following categories: externals, function, labels, classes, and namespaces. The root of the symbol tree is the global namespace, where namespaces define a scope such that the symbol names are unique within the namespace. The type of namespaces that Ghidra support are global, external, function, class, and generic namespaces that reside in the global namespace. Note that in software engineering, every namespace has an associated symbol. Now let us exploit Ghidra's auto-identified functionalities in order to compare it with the functionalities we identified while exploring the graphic user interface of the refor keylogger during the implementation phase. Click on the function folder listed in the symbol tree panel in order to check out all the functionalities Ghidra discovered in the refor keylogger source code. You can choose to click any of the outlined functionalities in order to review that particular function script, which is located in the source code being displayed in the listing display panel, as being displayed on my screen. Due to the large volume of the identified functions embedded in the refor keylogger source code, I wouldn't be able to go through all the functions with you, but I am encouraging you to go through all the outline functions Ghidra has identified in the refor keylogger source code and compare them with the functions that we discovered through the graphic user interface of the refor keylogger during the implementation phase, in order to determine if there may be any hidden functions embedded in the refor keylogger software. Let's now switch to the source code of the refor keylogger in the listing display panel in order to identify some of its embedded functions. Take a look at the left side of the source code. As I'm scrolling through the source code, you'll notice that there are some arrows indication at the left side of the source code. These arrows are referred to as flow arrows and are there to graphically illustrate the flow of execution within a function. And if you take a careful look at the flow arrows, you'll notice that they are of two different types. One of the type of the flow arrow is made up of dashed lines. The dash flow arrows are referred to as conditional jumps, while the flow arrows, which is made up of solid lines, is referred to as unconditional jumps. By default, flow arrows are only shown either at the start or at the end of a visible address. That is why as I scroll through the source code, you'll notice the flow arrows appearing and disappearing, just as the addresses embedded in the source code also appears and disappears as I'm scrolling through the source code. You can select an arrow by clicking it with the mouse in order to keep it from disappearing as you scroll through the source code. Note that selected arrows appears in green color as being displayed on my screen. In order to navigate to the endpoint of a flow arrow, simply double-click that particular arrow. And in the case where the cursor happens to be at the endpoint of an address, equally double-click the arrow of that particular address in order to navigate to the start point of the arrow. You can drag the border between the panel displaying the flow arrows and the main code browser panel in order to resize the flow arrows as I am illustrating. To hide the flow arrows, simply drag the border until it's no longer visible. Note that flow arrows automatically disappear themselves when they are no longer visible. Now to the main code browser panel. At a careful look of the source code as I scroll through it, you'll notice a plus sign just at the beginning of some of the script. These plus signs are indicating that there are some hidden content of structures and arrays which will be displayed upon clicking on these plus signs. Now let's check out Ghidra's auto-generated structure flowchart, which has been generated from the refor keylogger source code. In order to see Ghidra's auto-designed structure flowchart, just highlight all the source code by pressing the Ctrl key with the A key on the keyboard. And then Click on the Display Function Graph button located on the taskbar. On your screen now is Ghidra's auto-design structure flowchart generated out of the source code of the REFOR keylogger. In order to see the relationship link in the process flow, just click on any of the structure chart. In order to know how the REFOR keylogger is designed to operate, and as well as the opportunity to compare the information you gathered in the implementation phase with this auto-design structured flowchart, in order to determine if indeed the REFOR keylogger has some hidden functionalities aside its officially outlined functionalities, I urge you to take some time to study this auto-design structured flowchart generated out of the source code of the REFOR keylogger by Ghidra. We will review this source code into details in the next lesson, that is, the analysis phase. The analysis phase of software reverse engineering. In lesson 5, I did state that the analysis phase of software reverse engineering is the stage where the source code of a software is carefully reviewed or analyzed for either of the following reasons. For the determination of a possible existence of a backdoor in the source code of the software. Another reason is to determine if there is a malicious code embedded in the source code of the software, or to determine if there are hidden functionalities of the software aside the software's officially outlined functionalities. Some of the hidden functionalities of a software may include the software stealing user data to a remote server, or if a software is converting its host device as a botnet device, or in order to crack or bypass the license requirements of the software, which by the way is illegal. Note that there are many other reasons aside these outlined purposes and reasons for the reviewing and the analyzation of a source code. But for the purpose of our illustration, I'll limit the objectives of analyzing the source code of the REFOR keylogger to these outlined objectives respectively, as displayed on the screen. In order for you to understand the encryptions in the assembly code Ghidra generated out of the executable file of the REFOR keylogger, let us go through the processes involved in the conversion of the executable file of the REFOR keylogger into its assembly code. Doing that, I also take the opportunity to explain into details the terms and the inscriptions found in the code. On your screen now is the first conventional process involved in the reversing of an executable program into its core code, which is the machine code. On the left side of the table is the source code of an executable C program, which is to display the inscription "Hello World" onto a screen. And on the right side is the assembly code representation of the source code of the executable Hello World C program. Note that the displayed assembly code is just a small segment of the assembly code for the Hello World program. So the first conventional process is that before an executable program file is converted into its machine code, it is first converted from its source code into an assembly code. So what this means is that during the reversing process of the executable file of the REFOR keylogger, the executable file of the REFOR keylogger was first converted from its executable form to its source code, then to its assembly code. To those who may not know what an assembly code is, an assembly code is a type of a low-level programming language that is intended to communicate directly with a computer's hardware. Note that an assembly code is designed to be readable by humans, meaning you can directly decide to code or design an executable program in an assembly code. But because designing a computer program directly in an assembly code takes more time and more typing, most software engineers prefer designing their programs in a compiling programming language, such as the C programming language, in Python and other high-level programming languages, instead of coding a computer program in an assembly code. Now this is the last and also the second conventional process involved in the reversing of an executable file into its core, which is the machine code. During the second conventional process, the assembly code, which is generated out of the source code of the executable file of the Hello World C program, is converted into an assembly bytecode. That is the machine code representing the binary opcode, which is a computer-readable code in zeros and ones. So in summary, the assembly code is the intermediate programming language link between the source code of a program and the machine code. And also a source code is a human-readable programming language, while an assembly code is both a human and a computer-readable programming language, which for the sake of better and easy understanding of the instructions of an assembly code by a computer then converts an assembly code into a computer-readable programming language, which is the machine code, made up of zeros and ones. For the purpose of fast and direct interpretation of the assembly code by a computer in its machine code format, software developers often indicate with an extension such as functions, strings, .text, .data, .bss, and other memory map formats, which part of the hardware components of a computer is supposed to act on a specific instructions. For instance, if a part of a program requires internet connection, for fast response and direct interpretation, a program's developer must outline the strings, the functions, or a memory map indicating the specific computer component which is supposed to process and facilitate the internet connection aspect of the program. The indication that is specifying a particular component of a computer is termed as linking. In other words, linking is the process in which references to externally defined objects like code and data are processed so as to make them operational. To simply put, linking fills in the necessary fields and informations an operating system needs to run a program. For practical understanding of linking, I have outlined the memory maps of the assembly code with a red marking at the left side of the table, which is the .text, .data, and the .bss, which are all indicating which part of a computer component is supposed to respond to a program. And on the right side of the table is the machine code version of the assembly code on the left side of the table. But for the easy and fast response of the commands of the memory map, the computer, through the conversion of the assembly code into its machine code, has denoted the commands of the memory maps in the form of a bytecode, which is directly sent to the computer's corresponding component of the outlined memory maps respectively. For better and detailed explanation of the memory map of the RE4 keylogger, I will use the source code of the RE4 keylogger to illustrate its memory mapping. It is important to note that the memory mapping and the arrangement of a program tree is not universal. It actually depends on the functionality and the structure of a software. From the program tree of the RE4 keylogger, the header is the first segment of the memory map of the RE4 keylogger. Headers contains and refers to supplemental data placed at the beginning of a block of a data being stored or transmitted. To filter the source code of the RE4 keylogger for only headers, simply click on the header file in the program tree panel. Second on the RE4 keylogger memory map is the .text segment, which is also known as the code segment. The .text segment contains all executable data instructions in the memory segment, which ends up in the flash memory. To simply put, the .text segment contains all executable machine codes. In order to filter for only the .text segments in this source code, just click on the .text file in the program tree panel. The .data segment is the third memory map of the RIFO keylogger. It contains the global variables and statistic variables that are initialized, and it starts right after the .text. In order to display only the .data segment in this source code, simply click on the .data file in the program tree panel. The .bss segment, which is also known as the uninitialized data segment, starts at the end of the data segment and contains both global and statistics variables that doesn't have an explicit initialization. The .bss also ends up in the RAM. Fourth on the memory map of the RIFO keylogger is the .idata segment, which holds the import directory, that is the .e data for export. The .idata segment is used by both .exes and .dll files and links to designate the imported and exported functions. The .tls session, which is the fifth memory map of the RIFO keylogger, is used to specify the size and initial content, which is managed using memory paging and its size to quantize a page size of 4 kilobytes on the x86 machines. The sixth memory mapping segment is the .outdata segment. This segment is used to store constant data, and it is the read-only version of the .data segment. The last memory map segment of the RIFO keylogger software is the .rsrc segment. The .rsrc segment contains all the resources for the model. Generally, the contents of the .rsrc segment are res files, which is produced by the resource compiler. It's important for you as a software reverse engineer to note that the main target of software reversing is to get to the assembled bytecode, which is the machine code of the software being reversed, in order to understand how the software is designed to work, its functionalities, and its representations. Meaning the source code of a software is not the main target of software reverse engineering. On the note of source code, let us learn about the differences between a source code and an object code, which in other words is referred to as a machine code. On your screen now is a diagram showing the differences between a source code and an object code. From this self-explanatory diagram, a source code is made up of both an assembly code and a high-level code such as a C programming language, Python, Visual Basic, Delphi, Perl, PHP, Ruby, C#, ECMA script, Java programming language, and etc. While an object code is made up of the byte code and a machine code, which consists of both executable files and library files. For more detailed explanation about the differences between a source code and an object code, I have compiled all the differences that exist between a source code and an object code in a table form as displayed on the screen. Note that computers are unable to directly understand a source code, but can simply understand and execute a machine code. Let me quickly walk you through the systematic processes involved when a computer program is executed on either a 32-bit architecture computer or a 64-bit architecture computer. The systematic process of the execution of a computer program is made up of 4 main stages. The first stage involved in the systematic process when a computer program is executed on a computer is that the instructions of the computer that is being executed is first fetched from the memory. The second stage is the fetched instructions is then decoded into commands inside the control unit. The third systematic process is that the decoded commands is then executed and processed by the arithmetic logic unit, which is the ALU. The fourth and also the last systematic process is that the result of the operation of the issued instruction is either stored into registers or the memory. But it's important to note that this systematic process, which involves the execution of a computer program, is the same systematic process for both a 32-bit system architecture computer and a 64-bit system architecture computer. But in terms of software reverse engineering, the approach in reviewing a 32-bit system architecture-based software and a 64-bit system architecture-based software is different. Though a 32-bit system architecture-based software can be installed on a 64-bit system architecture-based computer through the manipulation of the environment variable of a 64-bit system architecture computer. Since the version of my Refor keylogger software is a 64-bit version, I will be reviewing its source code using a 64-bit approach and techniques. For this reason, I will only cover the approach and techniques used in reviewing a 64-bit system architecture software. That is, registers, instructions, stacks, addressing modes, and other features in relation to a 64-bit system architecture computer software, which I believe will not just enable and equip you to be able to review an assembly code of a 64-bit system architecture software. It will equally make you understand how the structure of a 64-bit system architecture-based software works, and as well as will enable you to identify registers, instructions, stacks, and addressing modes in an assembly code. Let's begin with the 64-bit system architecture registers. A register is a type of a computer memory used to quickly accept, store, and to transfer data and instructions that are being used intermediately by a CPU. In relation to a 64-bit system architecture assembly, it often uses either a 16-bit or a 64-bit general-purpose registers in its assembly. On your screen now is a table representing the various mnemonics of registers of a 64-bit system architecture program. As is indicated in the table, each register is represented with different mnemonics based on their size. Another observation about this table is that each register is designed to operate on different levels based on their respective representations, as is shown in the table. It's important to note that aside these registers, there are special purpose registers. One example of a special purpose register is the RIP instruction pointer, which is used to point to the next instruction to be executed in an assembly code. The RIP special purpose register has a 64-bit width. Another special purpose register is the R flags register, which is used in storing different conditional flags which is set during an arithmetical operation or sometimes used for a processor flow control. The FPR7 register is also another special purpose register used for floating point status and control registers. Last on my list of special purpose register is the RBP-RSP special purpose register, which is purposely used for stack manipulation and usage. All these outline registers are all 64-bit system architecture registers. So anytime you spot any of these registers in either an assembly code or in a source code, you should be able to tell that the assembly code or the source code you are about to review is a 64-bit system architecture-based software. Let us now learn about the 64-bit system architecture instructions. To those who may not know what an instruction is a statement that is executed at runtime. In other words, an instruction is used to define the operation being performed by the CPU. Such operations may include addition, subtraction, multiplication, and etc. It's important to note that instructions can have multiple operands to define the argument for a specified operation. To those of you who may not know what an operand is a part of a computer instruction which specifies what data is to be manipulated or operated on, while at the same time is representing the data itself. Also note that a 64-bit system architecture instruction statement can be made up of 4 parts, namely the label part, which is optional, the instruction part, which is required, the operand part, which is used for specific instructions, and lastly, the comment part, which is optional. The 64-bit system architecture has a large number of available instructions, but we will focus on the commonly used ones. One of the commonly used 64-bit system architecture instruction is the move instruction, which moves data from one register to another or from a memory location to a register. On your screen now are typical examples of how the move instruction is used in an assembly code. From these examples, you will notice that the second example is different from that of the first example, with the RCX 64-bit register of the second example being in a bracket. The meaning of the bracketed RCX 64-bit register is that instead of moving the actual data value from the RCX 64-bit register to the RAX 64-bit register, the address of the data value of the RCX register should rather be moved into the RAX 64-bit register. To simply put, the bracket around the RCX 64-bit register is indicating that the data value of the RCX 64-bit register shouldn't be moved into the RAX 64-bit register. Instead, its location address should rather be pointed to the RAX 64-bit register. It's important to note that both the RAX and RCX 64-bit registers are all examples of general-purpose registers. The addition and the subtraction instructions is another set of common instructions. The function of the addition instruction is to add two values together, but stores the result of the added values inside the first argument, which is the first value. This is a typical example of how the addition instruction is used in an assembly code. This code is set to add both the value of the RAX register to the value of the BRX register, but its outcome will be stored in the RAX register, meaning at the end of the execution of this code, the value of the ARX register will be made up of the original value of the ARX register plus the value of the BRX register plus the outcome of the addition of both the value of the RAX register and the value of the BRX register. In relation to the subtraction instruction, the value of the second operand is subtracted from the first operand, and the result is also stored in the first operand, just as that of the addition instruction. So always bear it in mind that both the addition and the subtraction instruction all stores its final results in the first operand or the first register. Third on our list of common set of instruction is the AN instruction and the XOR instruction. The operations of both the AND instruction and the XOR instruction are common with digital logic, so those of you who are familiar with digital logic may know about these operations. And just as the addition instruction, the subtraction instruction, and the move instruction, The AND instruction and the XOR instruction also stores its result in the first operand when used to perform binary operations on two operands. The XOR instruction can be used to reverse selected bits in an operand while preserving the remaining bits of the operand. The fourth on our list of common set of instructions is the jump instruction and the call instruction. The jump instruction is used to change the code being executed and also used to modify the value in a EIP or RIP instruction pointer. To simply put, the jump instruction causes a section of an assembly code to jump to another pointer location in the code. While the call function is used to implement function calls in order to fix up and push a RBP and a RIP instructions onto a stack appropriately before it is jumped to a new location. The difference between the jump and the call instruction is that in the case of the call instruction, when a call instruction is done calling a function, it actually knows the location to jump back to. On my list of common set of instruction is the compare instruction, which is denoted as CMP. The compare instruction is used to perform a compare operation by subtracting the operand that is provided, but except that there is no storage space with the compare instruction. For this reason, the result of the compare instruction is never stored. But if in case there should be an overflow in relation to the result of the subtraction operation of the compare instruction, the flag fields in the R flags register will be set. Note that bits found in flag registers are very important because the jump instructions has different variants that check those flags before performing the jump instructions. This is an example of how the compare instruction is used in an assembly code. What this code of compare instruction means is that the RAX register contains 0, and if we subtract 3 from the 0, the jump 0 instruction will then return. But if the flag is not set, the jump 0 instruction wouldn't return, meaning it wouldn't modify the EIP. Let's now talk about the 64-bit system architecture stack. A stack is defined as a data structure containing elements such as functions and other various operations in a contiguous memory. For the purpose of our illustration, I will only talk about two specific instructions that interact with stack. That is the pop instruction that reads from the stack and the push instruction which writes to the stack. In relation to the push instruction grows the stack by 8 and stores the operand content on the stack. This is a typical example of how the push instruction is used in an assembly code in order to grow the stack by 8 for the storage of the operand content on the stack. On your screen now is a typical example of how the pop instruction is used in an assembly code. In the case of the pop instruction loads the value pointed by the RSP register into the operand, meaning the pop instruction does the exact opposite of the push instruction. For better understanding of how the stack works, this is an animation demonstration of how the pop instruction and the push instruction works. To the left is the sequence of instructions, that is the push RAX, push RBX, and the push RCX. In this demonstration, all the sequence of instructions which has been outlined on the screen will all be pushed under the stack, and then we'll pop the value from the stack into the RAX register. So upon initiating the first instruction, the RAX register is pushed under the stack. And upon the second instruction execution, the RBX register is equally pushed under the stack. Upon the execution of the third instruction, the RCX is then pushed onto the stack. But upon the last instruction, which is the pop RAX instruction, the program then pops whatever value is on top of the stack and then stores it on the RAX register. So at the end of the execution of all the instructions, this is the final result of the stack. Note that the stack is important for understanding how functions are called later and often used to store local variables. The addressing mode of a 64-bit system architecture software is the last 64-bit system architecture feature we'll be covering. One may ask, what is an addressing mode? An addressing mode is used to specify how to calculate the effective memory address of an operand by using the information held in the register's contents contained within the machine instruction. Meaning an addressing mode instruction can access registers and memory in various modes. This is a practical example of how an addressing mode is used in an assembly code. What this code is instructing to do is to add the value of the RAX register to 14, and then is to store the results in the RAX register. You can also perform an addressing mode instruction on a register-to-register basis like this example. With this particular example, the value of the RAX register is cleared. An addressing mode instruction can also be used in an indirect access instruction like this example, which is instructing the addition of the value pointed to by the RBX into the RAX register. Another example of how an addressing mode instruction can be used is this. This addressing mode instruction code is instructing a move of the address 8* RAX plus RCX plus 12345 into the RBX register. It is important to note that anytime you see a value in a bracket in an addressing mode instruction code, it is indicating that the value in the bracket is a pointer, meaning the value in the bracket is a reference of an address location. I have animated this instruction exercise, which consists of all the instructions we've covered so far in this lesson. The first instruction is to move the 2FFF into the RAX register, and upon the execution, this is the result. The second instruction is to move the value into the RBX register, and upon executing, this is the result. The third instruction is to add the two values, which is the value of the RAX register and the value in the RBX register, into the RAX register. Take note of the results table. You'll notice that as I execute the third instruction, the value in the ARX register will increase from 2FFF to 3FFF. The fourth instruction is to move 10,000 into the RCX register. And this is the outcome as I executed this instruction. The fifth instruction is to subtract the value of RAX register from the value of the RCX register. But its result will be stored in the RCX register, since the RCX register is the first operand. And as I execute the fifth instruction on my computer, you will notice that the results of the RCX register will change from 10,000 to C001 on the results table. The sixth instruction is to add the value of RCX register to the value of the RBX register. And since the RCX register is the first operand, the result of the addition of the value of the RCX register and the value of the RBX register will be stored in the RCX register. The seventh instruction, which is a compare instruction, is to compare the value in the RAX register with that of the RBX register. And from the results table, the value in the RAX register is greater than that of the RBX register. The result of the execution of the 7th instruction is based on the condition of the 8th instruction, which is a jump instruction requesting a jump only if the greater than flag has been set. And since the value in the RAX register is greater than the value in the RBX register, the command will jump to the last instruction, which is the move RAX 0 by 1, and then the command will return to begin the process again. I hope with this example you now have a better understanding of how the instruction operates in a code. We had to go through the basics of how the registers, instructions, stacks, and the addressing modes of a 64-bit system architecture software works, in order for you to have a better understanding of the underlying assembly code, though Ghidra has a decompiler. Let's begin the analyzation phase of the reversing of the refor keylogger by first reviewing the source code of the refor keylogger for the purpose of identifying if there is any possible existence of a backdoor as our first objective of the analyzation phase. Before we begin with the practical session, which is the reviewing of the source code of the refor keylogger, let us first learn about backdoors in order to have a better understanding about backdoors, how it works, its types, and how to easily identify them. A backdoor is a type of malware that negates normal authentication procedures in order to access a cyber system, which could be a software, a hardware device, or a network. But often in the context of hardware devices and networking infrastructure, backdoors are mostly in the form of a software. To simply put, a backdoor is a malware or a malicious script which secretly allows access into a cyber system. So this is how a backdoor of a system works. It works by granting its creator or a cyber adversary the remote access to a system network or the resources within an application such as databases and file servers, the ability to remotely issue system commands, and sometimes to even update the malware or the backdoor itself. Types of backdoors. There are two main types of backdoors, but of many forms. The two main types of backdoors are the conventional backdoors, which are often hidden parameters or redundant interfaces which requires human authentication or authorization for its activation. Most conventional backdoors are often protected by password authentications, which has an administrative interface. That actually makes conventional backdoors vulnerable to brute force attacks, dictionary attacks, and lockout attacks, depending on the system architecture. So anytime you come across a conventional backdoor, just exploit it with either a password brute force attack, a password dictionary attack, or a lockout attack. Note that a conventional backdoor can easily be detected by a knowledgeable, skillful, and a smart cybersecurity researcher. The second type of backdoor is the unconventional backdoor. Unconventional backdoors are types of backdoors that require the authentication and the authorization between system applications and hardware components for its activation, making unconventional backdoors very difficult to detect, difficult to fix, and sometimes almost impossible to even fix. I consider unconventional backdoors as the most dangerous backdoors and also a zero-day exploit, which can be exploited by any cyber adversary for a very long time. Now that we know the various types of backdoors, let us now identify the various forms of backdoors. Forms of backdoors. There are three main forms of backdoors. First on the list of forms of backdoors is crypto backdoor. Crypto backdoors are backdoors designed as a weaknesses for a particular key message or prompt. The second form of backdoor is system backdoors. A system backdoor is a malware design backdoor designed to compromise a system infrastructure. This particular form of backdoor often relies on social engineering attacks for its initial execution. The last and the third form of backdoor on our list is application backdoor. Application backdoors are modified legitimate programs designed to bypass security mechanisms. Application backdoors are often inserted by those who have legitimate access to a source code or the distribution binaries of a legitimate program, which is already in use or running on a system. So anytime you happen to discover an application backdoor in an application, doing a software reverse engineering, look no further in search of its source, since it can only be inserted by an IT staffer or mostly the developer of the said application. Since an IT staffer and an application developer both have easy access and legitimate access to both the source code of the application and the distribution binaries of the application. But also bear in mind that hackers can equally plant an application backdoor into an application. That is only if a hacker has access to both the source code and the distribution binaries of the application. Application backdoors are actually very difficult to identify within a system, since it's a legitimate application known by a system, and they can easily result in system compromise as well. To those of you who prefer downloading paid applications and media files from torrent sites, I advise you to stop, because almost all the applications and media files which are uploaded onto torrent sites all have application backdoors embedded on them. Let us take a quick look at targets of application backdoors. On the screen now are targets of application backdoors. First on the list is web applications, followed by server applications, then network appliances, and operating systems. Based on the detailed explanation of system backdoors, its types, its targets, and how it's designed to work, I believe we can now proceed to review the source code of the refor keylogger for the purpose of identifying any possible backdoor embedded into its source code. To those who are new to software reverse engineering and the reviewing of source code and binaries of programming, I'll try as much as possible to explain into details all the relevant programming inscriptions in the refor keylogger source code during the reviewing process. But I wouldn't be able to review this source code on line basis, since this source code has over 5,000 lines, which will take us about approximately 2 to 3 days to complete the reviewing of this source code. But I believe with the detailed explanation of all the relevant programming inscriptions of this source code, you'll be well equipped to review this source code all by yourself. Before analyzing the assembly code of the refor keylogger, let me first explain the various column arrangements in this assembly code. The first column, which is made up of all digits, is known as the address field. It represents the memory address where a particular data is located. This second column, as I've indicated, is the raw byte column. This is representing the machine code instructions of the memory address. The third column is the mnemonic field. This represents the instructions that has been disassembled from the opcode. The fourth is the operands, which is representing either the register or the memory location used by the instruction. This is the xrefs, and it stands for cross-reference. This column is indicating that other locations of instructions has been referenced to an address. In order to navigate between two marked cross-references, just double-click on any of them. One unique and great feature about Ghidra is its ability to decompile an assembly code. This comes in handy for those who are unable to read and understand an assembly code. In order to convert an assembly instruction to a C code, just highlight the section of the assembly instruction that you would like to convert into the C language, and then click on the Decompiler tab. Before Ghidra converts an assembly instruction to a C code, it first uses its P code to abstract the assembly instruction into a P code operations. To those who are wondering what a P code is, a P code is an intermediate language which is shared across all processes. This is possible because all processes are created and programmed with a SLA language. For more detailed scrutiny of an assembly instruction, you can decide to use the byte view by just selecting the section of the assembly instruction you want to scrutinize, and then proceed to click on the byte view tab. For the easy identification and the filtering of the various functions and strings in an assembly code, you can use the Define Strings tab. From 15 years experience in reviewing source code, I know some common strings that most software engineers often use to hide their backdoor. So from my experience, I want us to search for some particular strings. And if we don't see any of those strings, then we'll have to spend more time to review the source code line by line in search of a backdoor, to see if the refor keylogger software has a backdoor. Since my version of the refor keylogger software is a Windows-based software, let me first search for the common control library string, which is actually a Windows processing file. Well, it seems the refer keylogger source code has a common control library string. Disclaimer: this doesn't mean that the refer keylogger software has a backdoor. It's just that this particular string is often used by software developers to hide backdoors. This is because the comctl32.dll file provides common Windows objects such as list boxes and combo boxes to Windows programs written in the Visual Basic language, and also the fact that it pertains to computer network security, which when deleted or removed, it will result in the non-functioning of the Windows operating system itself and other Windows programs written in Visual Basic. For this reason, most anti-malware and antivirus softwares either skip or refuse to scan the comctl32.dll string file during malware scanning. Note that Windows strings which are found in source codes are often designed to just make changes in the original Windows default strings, but a more sophisticated strings can be designed to replace the default Windows string file. But in this case, such strings, in addition to a malicious script, also have the same data as the string it will be replacing. In relation to the interpretation of the comcontrol32.dll string as assembly instruction session, the 00419D70 is the memory address location of the common control library data, while the second field, which is the raw byte data, is representing the machine code instructions of the memory address of the comctl32.dll string. In order to see the full raw byte code, just highlight on the session and then click on the Define Bytecode button. If in case you would like to affirm if the raw bytecode is indeed representing the comcontrol32.dll string, just copy the raw bytecode into any hexadecimal converter. Back to the source code of the refer keylogger. The third field, which is the mnemonic field, is represented with the data segment register. The function of the DS register is to store the starting address of the common control library data segment. On this note, I highly recommend you to always research about identified strings and registers in a source code in order to determine why it's being used and to know more about its functionalities. That is if in case you have no knowledge about it. As I said earlier, because the refer keylogger is a well-known and a patronized keylogger software, I'm limited to perform more detailed analysis on its source code, but I'll be spending more time to do so during my software reverse engineering bootcamp. But I believe with the detailed explanations of the methodologies and the procedures involved in software reverse engineering, I have equipped you enough to perform a detailed analysis on strings, registers, and instructions of a source code. Now let's move on to the third objective of reviewing this source code. That is for the identification of any possible malicious script. As I scroll through the source code, you'll notice that some of the source code inscriptions are red color coded. By default, Ghidra flags all encrypted, suspicious or malicious scripts in a red colored coded inscription. So anytime you are performing a reverse engineering with Ghidra and you come across red color coded inscription in the source code, know that Ghidra in its own patterns and during the analyzation of the source code, either identify that particular assembly instruction as encrypted, suspicious or malicious. It doesn't mean that if there is no red color inscription in a source code, that source code has no malicious script. More sophisticated malicious scripts are not easy to be detected for flagging. For this reason, I advise you to always analyze every source code line. Let us now randomly pick any of the red color coded inscription section to analyze it in order to determine if it has been flagged and red color coded for the purpose of it being either an encrypted session it being a malicious script or just a suspicious script. Before we begin to analyze this flagged assembly code, let me show you a trick to simply determine if a section of an assembly code has been flagged for the purpose of it being encrypted. The trick to determine if a section of an assembly code is flagged as a result of it being encrypted is to simply place the cursor of the mouse on the red color code inscription. And if there's a pop-up note like this, containing either an embedded or an encrypted data, then the section of the assembly code was flagged as a result of it being encrypted. To those of you who can code in and interpret an assembly code, you can choose to go ahead with the interpretation of this session. But for the sake of those who are unable to code and interpret an assembly code, you can choose to convert this assembly code to either a C code or a machine code. But for the purpose of this illustration, let's convert this assembly code into a C programming language in order to have a better understanding and an alternative interpretation of this particular assembly code instruction. Just at the look of these two different interpretations, you can easily deduce that both interpretations are way different from each other. But that of the C programming language is more simpler than that of the assembly code. In relation to the interpretation of the highlighted assembly code instruction in C programming language, the second line in the C code is just a warning comment, while the fourth line of the C code is a conditional call instruction, demanding a return of the rule of a Boolean variable, that is, if a statement is either true or false. The enum calendar info xw function in the fifth line is used to receive a calendar identifier in addition to the calendar's information from the parameters listed within the bracket. It is important to note that any application that is designed to be executed on only Windows Vista and later versions of Windows operating systems is using the enum calendar info xx function in preference to the enum calendar info function. The first parameter in the bracket, that is the call info underscore enum pro cw ip call info enum proc parameter, is pointing to an application which is a defined callback function, while the lcid parameter is representing the source language in which the calendar information should be displayed in, that is, if it should be displayed in English or any other language. The next parameter is the calendar identifier. The calendar identifier is specifying the type of calendar information to be requested. That is, if the calendar information should be made up of the day, the month, the year, or the time of an event. While the call type parameter is specifying the type of calendar information to be called. The instructions beginning from the 7th line to the 14th line is requesting that if the Boolean bvar1 variable is equal to the value in the enum calendar info w syntax, then the program should return bvar1. In summary, this section of the assembly code is to simply fetch specific date and calendar information. This kernel32.dll function here is a function used to call the enum calendar info x function. So based on our findings and the interpretation of this section of the assembly code, both the kernel32.dll function and the enum calendar info x function are all red colored coded by Ghidra because they both have hidden instructions concealed in them and not because they are malicious or encrypted. I believe that with this detailed guideline and simplified explanation on how to analyze the red color code instruction, you can easily analyze the rest of the red flag assembly instructions. But if in case you get stuck with any of the functions, just research or Google about that particular function in order to know how it works and its related syntax. In relation to the side effects and the vulnerabilities of the refor keylogger software based on its source code, I am limited to give much details about it, since the refor keylogger software is a commercial software, so I wouldn't want to face any lawsuit or discourage its users from downloading or purchasing it. But note that any listed Windows default registry keys and files that has been outlined in the refor keylogger source code has a high tendency of it being vulnerable, which in the documentation phase, I will disclose in the reviewing summary report of the RE4 Keylogger software. Let's now review the RE4 Keylogger source code in order to identify the software's license requirement assembly session. At the beginning of this lesson, I stated that I will only point out the part of the assembly instruction session which is instructing a user to either license or register the RE4 Keylogger software. And in addition, we'll only talk about how to crack and bypass the license requirements of this software. But for more detailed explanation and technical know-how on how to bypass or crack any software license requirement, I encourage you to join my Master Source Code Reviewing and Software Reverse Engineering Bootcamp course. Before I point out the parts of the session of the assembly instruction which demands a user to either license or register the RE4 Keylogger software, let's first learn about the various types of software licenses. In general, there are 5 main types of common software licensing models. 4 out of the 5 main types are examples of open source licenses, which allows a user to reuse the code for a period of time, while the other type of software licensing model prevents a user from reusing a software registration code or a software license key. One of the 4 open source license models is the public domain license model. The public domain license model is the most permissive type of software license model. When a software is in the public domain, anyone can modify it and use the software without any restriction. But as a software reverse engineer, I advise you to always analyze the software in order to make sure that it is secured before adding it to your own code base. It is important to note that a software code that doesn't have an explicit license is not automatically in the public domain. This includes software code snippets you find on the internet. The permissive software license is one of the 4 open source license models. The permissive software license is also known as the Apache style or the BSD style. This particular type of open source license model contains minimal requirements about how a software can be modified or redistributed, and perhaps is the most popular software license model used with free and open source software. Aside the Apache license and the BSD license, another common variant of the permissive software license is the MIT license. The Laser General Public License is another type of software license which allows you to link an open source libraries in the software. If you simply compile or link a Laser General Public License library with your own code, you can release your software application under any license that you want, even as a proprietary license. But if you modify the library or copy part of it into your own code, you would have to release your application under similar terms as the Laser General Public License. The 4th open source license model is the copyleft license, which is also known as the reciprocal license or the restrictive license. The most well-known examples of a copyleft or a reciprocal license is the General Public License and the Creative Commons Share Alike licenses. These licenses allows you to modify the license code and distribute new works based on it, as long as you distribute any new works or adaptations under the same software license. For example, a component license may be free to use and to be distributed for personal use only, but any derivative that you may create with a component license will also be limited to personal use only. The catch here is that the users of your software would also have the right to modify the code. Therefore, you would have to make your own source code available. But of course, exposing your source code may not be in your best interest. The last type of software license model, which also happens to be the only non-open source software license, is the proprietary software license. The proprietary software license is the most restrictive software license. The idea behind the proprietary software license is that all software rights are reserved, and as a result, such softwares may not be modified or redistributed by a third party. Now that we have learned about the various types of software license models, I advise you to always make sure that a software you seek to crack or bypass its licensing requirements is an open source software and not a software with a proprietary software license. Since the owner of a proprietary software license can sue you in the law court for modification or for the redistribution of his or her software without his approval.
Purchase your tracks today. Swatsy beats. Swatsy beats.
It beats coins on the beats.
Purchase your tracks today. with your chest. Careless wait for me. Sweaty beat. Sweaty beat.